Okay, welcome everyone to this seminar of the YRQG series. Today our speaker is Sebastian Zell. Sebastian studied at the LMU Munich, where he also did his PhD in 2019 under Jihad Wali. Afterwards, Sebastian held postdoc positions at the EPFL Lausanne until 2022 and moved then to the UC Louvain, where he's currently a postdoc. He worked on many topics around fundamental questions of cosmology and quantum gravity. And today, Sebastian will tell us about evaporating black holes, new quantum analogues, and a breakdown of classicality. So thanks a lot for following our invitation, Sebastian, and please take it away whenever you feel ready to start.
Yeah, thanks a lot, Tobias, for this very nice introduction. I'm very happy to be here and for this invitation. And so, as I said, so from my side, you can ask questions whenever you feel appropriate. And yeah, there's a lot of things to discuss here. And so, yeah, I'm very happy to give this talk. So this is based on work with Jihad Wali, Lukas Eisenmann, and Marco Michel. And so the three papers shown at the bottom. And the starting question is very simple. So let's look at a black hole, so the big black thing here, and then let's consider its evaporation, so the red wiggly lines. And then as a black hole evaporates, what happens to the black hole? And then you may say this is a stupid question. So of course it becomes a smaller black hole, right? What else could it be? And then the point of my talk, and that is almost the whole message of the talk, this is not so clear. So there's no conclusive evidence that indeed it becomes a smaller black hole, and I would argue on the contrary that there are good arguments why the black hole, as it evaporates, becomes an object that is no longer a classical black hole. And so that is the leading question for this talk: what becomes of an evaporating black hole? And there will be 4 parts that are also slightly modular depending on discussions and timing. And so first I was asked to give a review. And so the first part will be just a review of black holes. And so I guess I won't say anything new in that. So maybe I will phrase it a bit differently than is commonly done, but that should be a review. And then the second part is about the specific calculation of Hawking evaporation. And in particular, I will ask the question, what are the assumptions behind it, and how long are these assumptions valid, and when can it break down? And then in the third part, and so the third part is then the really original part, I will try to answer this question: what becomes of a black hole using analog quantum systems? And then in the fourth part, there's an outlook, also something about primordial black holes and de Sitter, if time allows. Right, so the first part, the review of black holes. So let's first consider a classical black hole. And throughout, I will consider Schwarzschild black holes, so there's no rotation and there's no charge. And then there's a single parameter that determines the black hole, that is its mass, m. And then, as you know, the geometry is set by this mass. So you multiply m by Newton's constant g, and that gives you the Schwarzschild radius of the black hole. And then this Schwarzschild radius is the only parameter in the Schwarzschild metric. So that fully determines the geometry of the black hole. And so what this means in particular, let's consider 3 different suns. So here that's indicated by 3 different colors. And all 3 suns have the same mass, but otherwise they have different properties, different spectrum, different color. And now for, let's say they all collapse to a black hole, as suns sometimes do. And then, because the black hole is only determined by the mass, it means all 3 different suns collapse to the same black hole. And that is then what goes under the name of the no-hair theorem. So saying that outside the horizon, classically, you only see the mass of the black hole and nothing else. And so all objects different objects of the same mass that collapse to a black hole will all collapse to the classically same black hole. And so, in fact, this observation is at the heart of all questions about black holes. Okay, so that is the classical black hole. And then let's go to the quantum black hole. So let's add quantum properties. And so there's two important and related properties. So the first one is the entropy, as discovered by Bekenstein. So the famous area law entropy of the black hole. So that the entropy of a black hole is Schwarzschild radius squared divided by Planck's constant and Newton's constant. And so Bekenstein derived this from the conservation of entropy. So if you have some object carry entropy, throw it into a black hole, then the whole entropy of the universe shouldn't decrease, and so the black hole should have entropy. And so that what that means is that the black holes black holes of the same mass are quantum mechanically distinct. So what does it mean to have an entropy? An entropy means that the same macrostate, so the same black hole of mass m, can be in different microstates. And so in e to the s different microstates. And so that entropy means quantum mechanically the black hole has another label. It's not only the mass, but there are some other properties that characterize the black hole. Second property of the black hole is then the famous Hawking particle production. So that it is this Hawking's famous prediction that black holes, in fact, once you take into account quantum effects, are not black, but they radiate, so they produce particles. And what is important for us here is the fact that this particle production is solely determined by the classical geometry. So that is all properties of these produced particles are solely determined by the classical geometry of the black hole, so they are solely determined by the mass of the black hole. And I will elaborate on this point. And then once you know that you only see the mass of the black hole, well, you only see the geometry. So really classically, the only quantity you see is the geometry, the Schwarzschild radius. And then without any calculation, you can do dimension analysis and you see the key properties of the Hawking particle production. So one is, so how often do you produce a particle? Well, the only way to form a rate is as 1 over the Schwarzschild radius. So the speed of light is 1. And so just by dimension analysis, the rate is 1 over the Schwarzschild radius. So each Schwarzschild time you produce a particle. And what is the mean energy of the particle? Well, the only length scale you have is the Schwarzschild radius. So the wavelength is the Schwarzschild radius, and then the energy is h bar over the Schwarzschild radius. And then, as you know, there's a thermal distribution around this mean energy, but that is, I would argue, not the essential property here. And then, of course, the explicit calculations will give you these results, but just, once you know it's only the geometry, then dimension analysis tells you that each Schwarzschild time you produce a particle of Schwarzschild length. And then you can immediately calculate what I would call the naive timescale of evaporation or half evaporation, so neglecting order 1 factors. So you know how often you emit a particle, you know how much energy the particle has, and then you can compute the timescale after which the energy of the produced particles becomes comparable to the mass of the black hole. So that is a one-line calculation just from the quantities shown here. And then you see this time scale is entropy times Schwarzschild radius. And then that is also by dimension analysis not surprising. So the only time scale I have is Schwarzschild radius. And then the only dimensionless quantity I can form is the entropy. And so you get this. So after you emit on the order of s particles, then the energy in the emitted particles is comparable to the energy of the black hole. And then, of course, energy should be conserved. And then that is then the time scale of evaporation, half evaporation. So far, so good. But now let's combine the two previous slides. So let's consider these three different suns, all of the same mass that collapse to a black hole. And then the black hole evaporates. And then we saw that the evaporation is only sensitive to the geometry, so to the Schwarzschild radius. And so it seems that all of these three different suns collapse to the same classical black hole, and then that emits the same radiation because the radiation only sees the mass. But that cannot be. So evidently, such a process would not be unitary. Yeah, I mean, there's different ways of phrasing it. I think the most intuitive way of unitarity is just saying that you can always have the film run backwards. So given the final state, you can just do time evolution with the negative, like with negative time, and you should be able to arrive to the initial state. And evidently you cannot do this here. So if all of them go to the same radiation, then there's no way of knowing from which of the three different suns did you start. And of course, there's the more formal way of phrasing it. Let me start from a pure state, and then the black hole Hawking's evaporation produces a mixed state, and then the pure state cannot evolve to a mixed state. So that is the more formal way of saying it. But yeah, for me, more intuitive is just saying, okay, if this were the case, then you cannot have the film run backwards, and that cannot be unitary. So information about the initial state is lost. So even if you can measure with arbitrary accuracy the final state, in this way you won't see the initial state. And of course, I mean, Hawking himself famously noted that immediately after his prediction of black hole evaporation. But yeah, where I'm going in this talk is then to ask the question: do we really know that? So is that picture, does that really follow from the equations that we have? And I will argue that it doesn't. So that within the regime of validity of our equations, everything is consistent, and then within this, but this regime of validity stops already quite early, and so within the semi-classical Hawking calculation, you cannot go to the final evaporation of the black hole. But yeah, okay. The question is, how long is Hawking evaporation valid? That is then the question, and then if it were valid too long, then you would get this unitarity problem, and then I will argue it's not valid so long, and so there's no unitarity problem. All right, that was already a small preview on the next section. So that for now was the review of black holes. So I don't know if there are any questions up to this point. Otherwise, there will be the discussion afterwards, as I understand. All right. Then let me go to the second part. Namely, now let's explore what are the assumptions behind Hawking evaporation and how long are they valid. So the Hawking's calculation is a semi-classical calculation. So it means you consider quantum fields in the background of a fixed metric. So you take the fixed Schwarzschild metric and then put quantized fields, so gravity and other fields on top of that. And then you compare the vacua in near horizon and asymptotic vacua, and that is how the calculation goes. I'm not going to show any details of the calculation, but the important point is just it's semi-classical. So that's sort of the only way, the only way we really know how to do to have this fixed background and then the quantum fields on top. And now, when is this exact? So when can I really do that? And so there's a unique limit in which I can do that. That is the semi-classical limit, in which So maybe let's read from right to left. So I want to keep the Schwarzschild radius fixed. So of course, because I want to have some specific geometry. And so it should be a limit that does not affect the geometry. But I want a limit where I can really treat the black hole as fixed. And so when can I do that? When I send the mass of the black hole to infinity. Because if it's an infinite mass black hole, then really it won't feel a back reaction. Then it's really unchanged under the effect of particle production. And then, okay, if I want to keep the Schwarzschild radius fixed with infinite mass, that means I have to send Newton's constant to 0. And of course, it's what I would call a fictitious limit. So of course, you cannot do this in the real world. In our world, there is some Newton's constant and there's no limit. But it's kind of a limit, like a Duncan experiment of different worlds. And so we imagine a world in which gravity is infinitely weak. And in this world, then the Hawking semi-classical calculation becomes exact. Yeah, how does it work? So evidently, the physical picture is just, okay, it's an infinite mass black hole, so it doesn't feel the back reaction. And then that also works out in terms of equations. So entropy in this limit goes to infinity. So Schwarzschild radius is fixed and also h bar is fixed, but g goes to 0, and so s goes to infinity. And then this timescale of evaporation, half evaporation, that is s times rg, also goes to infinity. Yeah, and so it's particle production by an eternal black hole. In pictures, it's very boring. I start from a black hole with mass m. It emits a particle, and then because m is infinite, it still has the same mass m, and it just keeps emitting forever. And that is the limit in which Hawking's calculation is exact. And evidently, there's no question about unitarity in this limit because the black hole never disappears. So you can just ascribe all information about the initial state to the black hole and say, okay, yeah. And especially, you also see that the entropy goes to infinity. So consistently, all information goes into the black hole and never comes out in this limit. But now we want to talk about finite mass black holes with finite Newton's constant. So black holes in the real world. And so let's, and in this, for the real black holes, evidently Hawking's calculation is only an approximation. And then let's see how good it is. So what is the parameter controlling the quality of the approximation? It is the degree to which the black hole mass is not infinite. And so how do I feel that? That means I compare the energy of a single emitted particle to the total energy of the black hole. So that is precisely the quantity that characterizes the back reaction. And then that should give me the correction to being an infinite mass black hole. And then no surprises here. So I compare two energy scales. So I get it's a dimensionless quantity, and then S is the only dimensionless quantity I can form. And so we expect that the semi-classical calculation is exact up to corrections that scale with 1 over S. And then this is good news. So evidently we are interested in big black holes. So masses that are much bigger than the Planck mass. And for these black holes, S is very large. So remember, for the astrophysically observed black holes, S is 10 to the 60, 10 to the 80 something. And so the S is very large, 1 over S is very small. And so indeed, the semi-classical calculation is a very good approximation. And so this is good. However, let's now look at the whole black hole lifetime. So we again start with a black hole of mass m. And then let's consider the first emission. So, okay, we just have one Hawking quantum. And then we said for this first emission, the semi-classical calculation is extremely accurate. And so, okay, we know that, okay, after timescale Schwarzschild radius, quantum of wavelength Schwarzschild radius will be emitted. And then the question is, what is the final state of the black hole? well, in the semi-classical picture, it's just a fixed background. So it's just a fixed black hole. And so it's still the same black hole. And then this is very accurate up to corrections of 1/s. But of course, we can do better. So energy should be conserved exactly. And so the mass of the black hole should shrink by 1/s. And then, of course, that is a completely negligible correction. But then by the same degree that the mass of the black hole changes, also other properties of the black hole can change. So there's so by the same degree, some non-classical properties of the black hole can emerge. And of course, they only emerge with 1/s. It's completely negligible. And so to extremely good approximation, that is still a classical black hole. And so I can still apply the semi-classical calculation for computing the next step of evaporation. So in the beginning of evaporation, there's no question. Certainly the semi-classical description is good, and we know what happens. But now let's see how long that goes. The crucial point appears when order 1 of the mass changes. So if you evaporate long enough, so on the order of S emissions, then the mass of the black hole changes appreciably. So let's take half mass for being definite. And evidently, so you see that, okay, the correction is 1/s to the mass per emission, and then I need S emissions to have an appreciable correction to the mass. But then to the same degree that the mass changes, so the mass deviates from being semi-classical, also other properties of the black hole can deviate. So after these S emissions, we get some object of mass, let's say m², but we don't know that it's a classical black hole. So remember, it's a quantum process that leads to the shrinking of the mass. And certainly you cannot appeal to the classical Noether theorem for saying that this is still a classical black hole. And so important to emphasize here, I'm not saying that it's not a classical black hole. I'm just saying the calculation doesn't tell you. So this is where the approximation, the semi-classical approximation breaks down. And so once the black hole mass changes order 1, you don't know what this object of mass m² is. So it could be a black hole, it could not be a black hole. I would argue there's no conclusive calculation either direction. So to formulate in a different way, the question is about the self-similarity of black hole evaporation. So let's compare two black holes, whatever you call it. So let's compare two situations. And one situation is you have a black hole of mass m, and then it evaporates until the object reaches m². So that is the situation I'm trying to show here. And let's compare that with a young black hole of mass m². So here both objects have the same mass, but one object was newly formed, and the other object you get from the evaporation of a larger black hole. So that is an old black hole and that is a young black hole. Both have the same mass. And then the question is, are these two objects the same? So is the old black hole like a young black hole? And let's just think it through, but let's just explore the two possibilities. If they are the same, then that is good because we know what the object is. So if the old black hole is still like a young black hole, then we know what it is, we can describe it, we know the geometry, and we also can compute evaporation according to our semi-classical calculation. However, then this process won't be unitary. Namely, it's precisely this m² point beyond which the semi-classical calculation runs into conflict with unitarity. So I can also elaborate on that. So just, I mean, Page's time, so Page's argument, just why m² is special. But yeah, just to say, so if in the initial steps of evaporation are semi-classical, that is completely compatible with unitarity. But if after losing half of the mass, it's still the semi-classical mixed evaporation, then this is incompatible with unitarity. And then conversely, if the old black hole is not like a young black hole, that is not good computationally, so we really don't know what that object is. But then there's no, so there's no contradiction with unitarity. And of course, okay, if the old black hole is not like a young black hole, then usually in the in-person seminar, this is where people get very uncomfortable and say, okay, this is still a large object. So of course, if you lose half the mass, then it's still a macroscopic object. It's no Planckian physics. And so you have a macroscopic quantum object. And then that is something you have to wrap your head around. So that is certainly something we haven't seen before. Just to give an like zeroth order intuition, what could this object be? So the zeroth order intuition is it could be a superposition of black holes. So that you say you consider black hole states of mass m½ with different positions, and then you form a superposition of that. So that would be the simplest way of forming some object that arises from a black hole, has the mass that you want, but is not a classical black hole. All right. Any questions at this point? So as I said, usually in the in-person seminar, that's when people start shouting. All right. And then let me emphasize again. I'm not saying I know. I'm just saying we don't know. That is the main message here of saying that just assuming that black hole evaporation is self-similar, in my opinion, is not justified. So this is an open question if it's self-similar or not, and then that is what one should seriously consider both possibilities and find arguments in either direction. And so yeah, of course there's some if you see it in front of your eyes like this, I would argue it's more conservative to say that it's not self-similar. So all of nature that we have observed is unitary. And then if I have two options, I don't know which one is true, but one is unitary and the other is not. Usually I will take the unitary option. So just because the rest of nature that we have observed is unitary. All right, and then
sorry, I have one question.
Yeah.
So then the issue, I guess, arises mostly when we reach masses that are getting closer to Planck mass.
No,
right?
no. That is there's
bigger
no
masses than that. So why is that? Because I would say I think the back reaction of the Hawking radiation like it isn't really big. So like how would this change this from like a regular black hole to a
Well, I mean, just in terms of the numbers, the back reaction of a single emission is 1/s, and that's extremely small. But you need S emissions to get to half the mass. And so it's S times 1/s. And that's how you get order 1 correction.
I see. Okay. Yeah, okay, sorry. Yep. Makes sense. Okay.
Oh, but thanks for the question. It's really important to point this out. Each single step has a very small correction, but you need a huge amount of steps to get to half the mass. And then it's exactly, you need S steps, each step with 1/s correction. And that is how you get the order.
You're talking about a step is oh wait, do I have my a step is a one emission of one particle of one in Hawking radiation.
Yeah.
Okay. Yeah, I see. Thank you.
And the point is that you need a huge number of Hawking emissions to lose half the mass. So
is there an easy way to see why this has to be steps equal to the entropy? Sorry, maybe it's a really silly question.
Yeah, so it's very easy to see. So you have the number of steps is the black hole mass divided by the energy of the single Hawking quantum.
Mhm.
So it's m
I can just invert it for m over 2 and then.
Yeah.
Sorry. Yeah. Okay. Thank you.
Sure. Yeah, and yeah, thanks for the question. So it's really important to point out it's not about Planckian physics. So these black holes are as big as you want. So if you want a non-classical black hole of mass m, start with a classical black hole of mass 2m. And then that is still the same order of magnitude of mass and still the same order of magnitude of the Schwarzschild radius. Of course, the great tragedy in terms of observations is that all black holes that we have observed are so large that they have, I mean, of course, we haven't observed any Hawking quantum, that is the other story, but for the black holes that we see, they have only emitted a few Hawking quanta at best. So they are still in the very first steps of their evaporation if they evaporate. But yeah, all of them are so big that yeah, they only have a few steps. So for them, certainly they are classical because it's the early stage of evaporation. Right. And then, okay, so here so I think, yeah, the second part is the one that is dearest to me, just saying, yeah, like what are the limits of our knowledge and what is the question we should ask. And now for the third part, let me come to the original work. So how we tried to address this question, what becomes of the black hole as it evaporates. And of course, the whole problem comes from the semi-classical limit. So in the semi-classical limit, you take the mass of the black hole to infinity. And so by construction, this limit shuts off back reaction. And so it's by the very construction of your computation, it can never be informative about the back reaction on the black hole. And so we somehow have to study evaporation without a semi-classical limit. And then that is not so easy. And one approach that people have been using to address this is to use analog systems. And so here I would define the analog system as a system that shares important properties with gravity, but is much more accessible both to computations and experiment. And of course, you always have to pay a price. It can never share all properties of gravity. If you have a system that shares all properties of gravity, it's gravity. And then you haven't changed the question. And so it's always some properties that you have to give up, and then other properties that you have to focus on. And then the first proposal in that direction, and the proposal that has become quite famous, is by Unruh, who observed that the geometry of the black hole, so the horizon, can be implemented in a non-relativistic fluid. So and then that is really it's a big connection. So on the one side, you really have the black hole, huge astrophysical, you can never observe. And then some properties you can implement in some tabletop experiments. So it's really, you put on some table in some lab the right kind of atoms, and then they will form the horizon. And then you get an analog of a black hole horizon. And so that, yeah, the sonic black hole analogues, what they are called. And it's a proposal that has been implemented in experiments. And now the direction on which I've been working is the orthogonal approach, I would say, where you forget about geometry and focus on the quantum properties of the black hole. So there's different quantum properties you can imitate. And so, yeah, so my approach will be to imitate some of the quantum properties of the black hole. And here I will present one concrete work in that direction, where we focus on the entropy of the black hole. And so, okay, the entropy, of course, is a quantum property. So you see h bar there. If you send h bar to 0, entropy will be infinite. So entropy is a quantum property. And then, as already said in the beginning, if you have an entropy S, then so yeah, on the quantum level, that means you should have an exponential number of microstates. So yeah, entropy, just microstate entropy being the logarithm of the number of microstates. And so if I want to have an object of entropy S, I need to have e to the s different microstates. And so what we've been doing is to look for the simplest system that can have such a large number of microstates. And then let me just concretely show you how that is done. So let's consider S different quantum modes. So quantum modes, just oscillator mode. So here I'm really going a large step away from gravity. So these are non-relativistic quantum oscillators. So that's really quantum mechanics 1. And so we take them to be bosonic, and then they have the usual canonical commutation relations between the annihilation and creation operator. And then we just take S of these oscillator modes. And then, of course, with S modes, you can form an exponential number of states. So let me just focus on, let me just take these as exemplary states. So we take a state where the first mode is occupied or not, and then the second mode is occupied or not, and the last mode is occupied or not. And then only these states are 2 to the s different states. And then, okay, exponential number of states. But of course, that cannot be so cheap. So what else do we need? Well, we want all of these different states to be microstates for the same macrostate. So all of them in particular must have the same energy or a very similar energy, so that I can count them as microstates for the same macrostate. And so that is the challenge. How can I achieve that exciting an oscillator mode doesn't cost energy? So usually you have to pay energy to excite a mode. And then how can I have S modes, and so that all of the S modes I can excite without energy cost? Let's write down the model. So here I'm just writing down the kinetic term for all these S modes. So that is just a free Hamiltonian for the non-relativistic oscillator. And so the sum of S free Hamiltonians. So as usual, I form the number operator as A dagger A. And then this is just the kinetic term, the free Hamiltonian. And I take some normalization here that, okay, I can also explain, but this is not super important for what I'm showing. And of course, if you just take the model like this, you have no entropy, because it costs an energy square root of S to excite one of the modes. And so the different states where the mode is excited or not have different energy, and you have no entropy. Then what's the trick? The trick is to add another mode. So here that I call N0. And then the N0 has also some kinetic energy. But the crucial part is the interaction between the N0 mode and all of the other modes. So this is a quartic interaction. So remember, the number operator is A dagger A. So this is a quartic interaction between the N0 mode and all of the NK modes. It's an attractive interaction. So it contributes negative into the Hamiltonian. And then I have chosen as interaction strength a very weak interaction of 1 over S. And now, why does that do the job? So if I now take some fixed background of the N0 mode, then the effective energy gap for all the NK modes is given by square root of S, my normalization, and then 1 minus occupation of N0 over S. So just evaluating the Hamiltonian for some occupation of N0, I see that the effective energy gaps for all the NK modes is like this. And so you see the positive contribution from the kinetic energy, but you also see a negative contribution from the interaction. And so it's an attractive interaction, it contributes negative to the energy. And then, of course, if I take the right occupation here, So if I take n0 equals S, then the effective energy gap of these nk modes is 0. And so that means on this state of so this high occupation of the n0, I can excite all of the nk modes without paying energy. And then that is how we get the entropy. So now on this particular state, I have an exponential number of states that are degenerate in energy. And so that's how I created microstates for my macro state n0 equals S. Yeah, and so here, okay, macro state then is set by the occupation of n0, and then on this state, all of the nk modes are effectively gapless, and that's how an entropy emerges. Let's do one more step to imitate the black hole. So let me take some external mode. So let me that I call NB here. So there could be some mode of some other field, and then this NB is allowed to exchange particle number with the A0. So this A0 now, yeah, can decay into NB modes and again with a certain interaction strength. And now this very simple model imitates the following properties of a black hole. So the n0 here, so the occupation of n0 is what sets the mass of the black hole. So that is some energy you have to pay. So just like forming a black hole costs some energy that you have to pay. And so the n0 sets the macro state, so sets the black hole mass. And then on a particular occupation, so if the n0 has this particular occupation S, then that is a black hole-like state, because then the nks carry entropy. So then all of the nk modes are gapless, and I can excite them. And then all these states that I showed in the beginning, so n1 excited or not, n2 excited or not, until ns excited or not, have the same energy. And so they are microstates for the black hole macro state. And the NB imitate the Hawking quanta. So you can convert some energy of the black hole. So you can decrease the mass of the black hole by creating Hawking quanta. And so with these very off-the-shelf components, we can imitate these black hole properties. Of course, yeah, I mean, there's many caveats now to this. So first of all, here, so this system only has a single black hole mass. So in this system, only the n0 equals S leads to a black hole state. So the spectrum of black hole states, there's only one black hole in the spectrum. And of course, gravity should have black holes with all kinds of masses in the spectrum. And so the first thing we need to do is to add another black hole state. And so I can show you in some additional discussion how that is done. So it's essentially just two copies of that Hamiltonian for two different values of S. And then what we do is a system that has two black hole states. So of course, that is not the continuum that we want, but then that is already a good place to start, where I then can start with a big black hole state. And then the spectrum features another small black hole state, and then I can see how to go from the big black hole to the small black hole. And that is exactly what we did. So we took the system that has two black holes in the spectrum. We take as initial state the large black hole state, and then we show, then we investigate if the system, or on what timescale the system evolves to the small black hole state. And the beauty of how we did that is that so the model I've been showing to you is really the non-relativistic quantum oscillators. So that has a finite Hilbert space, and then if for appropriate parameter choices, you can compute the exact time evolution. And so here I really want to emphasize how amazing that is from a high energy perspective. So in high energy, we always have some approximations and small couplings and whatnot. And here for this system, you can really compute the full time evolution. So you compute e to the minus iht times the initial state. And so that is just the full answer. There's no approximation. There's no, it's just the full non-perturbative time evolution. So we really know what happens in that model. And in that model, what we see is a slowdown of evaporation. So we see that it's very hard to get from the big black hole state to the small black hole state. And so usually the system doesn't go at all. And then if it does, then it goes on a time scale that is much longer than the time scale given by Hawking evaporation. So yeah, and so and of course that is to be compared with the time scale of Hawking evaporation, so the rate of energy loss. And so we see that often the system doesn't go at all, and if it goes in that direction, it does so very, very slowly. And then remember, S is a huge quantity for any realistic black hole, and so that is an enormous slowdown of evaporation. And then let me qualify the statement. So in the analog model, that is what we see. That is exact. And then the question is, to what extent can you carry this back to the black hole? So of course, this analog system has some similarities with the black hole, entropy, Hawking evaporation, but of course it's not a black hole by any means. And then this is the usual caveat for all analog systems. You observe something in the analog system. In the analog system, you know what happens. If that property carries over to the black hole, no one knows. So that is, of course, it is always an indication. So that is always the price you have to pay for being analog. But yeah, in our analog model, we see the slowdown, no questions asked. And then that is an indication that the same thing could happen for the real black hole. And then in a second model, so there we imitate some different properties. We studied the question, when do you see the deviation from the semi-classical description? And in that model, we saw again, the same story. In that model, we see that the classical description breaks down after square root of S times Rg, which is much, much smaller than S times Rg. So that is a breakdown of the classical description even much earlier than losing half of the mass. And that is what we see in the model. And then does it also happen for a black hole? Remains to be seen. But the analog models give indications for an early breakdown of the classical description. So that is, I mean, square root of S is still many steps of emission, but it's many steps before m half. So it's much before losing half of the mass. And an indication that at this point, evaporation could slow down drastically. Right. So I don't know how fast I should wrap up. My watch says it's.
I think take your time. Right. We have time, plenty of time for discussion afterwards still.
All right. Okay, it's just two more Outlook slides, but then I will take my time on that. So as I said in the previous part, so from the analog models, we see this indication for an early breakdown of the classical description that could lead to a drastic slowdown of evaporation. Let's see how we could observe that, or how to test this hypothesis. And of course, the ideal testing ground for that are primordial black holes, because the smaller the black hole is, then the smaller the entropy is, and so the faster the evaporation and the fewer steps you need until you see a possible breakdown of the classical description. And then just give you a brief background on primordial black holes. So if black hole evolution is self-similar, then so you can apply Hawking's calculation throughout. Then there's the famous what they call Hawking bound, that black holes below approximately 10 to the 15 gram would have disappeared by today. So just the smaller the black hole, the faster it evaporates, and then you can compute that if Hawking is valid throughout, then below 10 to the 15 gram they would have disappeared by today. And so, of course, that's then what people call the Hawking bound, and say, okay, if primordial black holes are dark matter, they should have more than 10 to the 15 grams, because we certainly see that dark matter is still around today. And now, if there's a slowdown, then much lighter black holes can have survived until today. And so remember the slowdown. So just parametrically, you see the slowdown can only happen by powers of S. S is huge, and so yeah, it's a drastic slowdown, and much lighter black holes could have survived until today. And then that has a twofold implication. So I would say the most important point here is just that if by some means you are able to measure just a single small primordial black hole that is still around today, then you've learned an amazing amount of about quantum gravity. So if you astrophysically detect some primordial black holes below 10 to the 15 gram that is still around today, then you know empirically that evaporation has slowed down, and then you have learned an amazing amount about quantum gravity. And amazingly, detecting the small primordial black hole is not crazy. So of course, it hasn't been done, and it's not easy, but people are not looking for small primordial black holes because they think they are forbidden, but people are looking for small compact objects in this mass range, and so that is something that it is conceivable. So it's not easy, but really looking for the small primordial black hole is something that is a realistic goal. And then the second implication, of course, if the evaporation slows down, then the constraints on primordial black holes change drastically. So that is, so in particular, the small primordial black holes become viable dark matter candidates. So there's this famous plot that you see at every primordial black hole talk, where, okay, on the x-axis, you have the mass of the primordial black hole. On the y-axis, you have the abundance, so the energy density in primordial black holes compared to the energy density in dark matter. Of course, that has to be smaller than 1, just because we know how much dark matter we have, and if it's equal to 1, then primordial black holes are all of dark matter. So the line here on the top is the line where primordial black holes are all of dark matter, and then there's all kinds of constraints from the CMB and from various astrophysical processes, and some of these constraints are also controversial, so I'm not taking anyone's side here, but I'm saying there's a lot of work in that and a lot of constraints. And then what you see on all of these plots is this 10 to the 15 gram, and then it cuts off because people say, okay, then the Hawking bound, so if Hawking evaporation is valid throughout the lifetime, then below 10 to the 15 gram can't have survived until today, and it can't be dark matter. And then here the point is that we don't know that, and it would be extremely interesting to look in this mass range. First, because that is a new window for dark matter, and second, because just detecting a single small primordial black hole, would carry this huge amount of information about quantum gravity. And then, since Tobias also said that, so there's also 2 recent papers on really exploring these constraints. So if there's a slowdown, what constraints do you still have? So there are still constraints, and what are viable mass ranges for these small primordial black holes with a slowdown of evaporation. And then just one outlook slide for cosmology. So from the perspective of the analog models, so from the perspective of entropy, and de Sitter and black holes are extremely similar. So de Sitter being the solution of GR in the presence of a cosmological constant, and that is extremely relevant for our universe because both the beginning and the end seem to be de Sitter. So inflation is a phase of quasi-de Sitter, so where the universe is very close to being de Sitter. And then the dark energy that we observe presently is de Sitter. So in the asymptotic future, it seems like we're going to a de Sitter state. And so that is a very relevant cosmological solution. And then as the black hole, it only has a single parameter. So in this case, we can take it as the Hubble frequency h. And then there's an analogon of the Hawking particle production, so the Gibbons-Hawking particle production de Sitter. also with rate, given that there's only one choice for the rate and for the energy of the produced particles. And then if you make the analogy of Rg going to Hubble radius, and then the entropy is also mapped 1-to-1 from the black hole to de Sitter. And so all of what I've been saying applies to de Sitter. So then also for de Sitter, there's the question, how long can it be described classically? So you produce particles that backreacts on the cosmological spacetime. No one knows how it backreacts. And then there's the question, how long can you describe de Sitter classically? And then there's also the analogon of Page's time. And so that we have also worked on. Then the quantum break time of de Sitter, saying that at the latest, when the energy of produced particles is comparable to the energy density of the cosmological patch, that's when the classical description of de Sitter should break down. And then, of course, that has many implications for excluding eternal inflation in the asymptotic past, or then how long can dark energy be described classically? All right, let me summarize. I've argued that the cumulative backreaction of evaporation can lead to a breakdown of the classical description of a black hole. And so, yeah, as has been said very nicely in the discussion, it's really the cumulative that is important here. The backreaction of each emission step is small, but if you have enough emission steps, that's when you start to feel the strong backreaction. And so the open questions are, how long is the classical description valid? And then if it breaks down, what happens after the breakdown? And then I use the analog models, so the quantum analogues that imitate quantum properties of a black hole, such as entropy, to show that there are indications for an early slowdown of evaporation. And then as a particular consequence, that makes small primordial black holes windows on quantum gravity. Thanks a lot.
Yeah, thank you very much for this very informative and clear talk. So let's maybe stop first the recording.